Today I'm going to present our work about world cuisines, a massive scale benchmark for multilingual and multicultural visual question answering on global cuisine. In this presentation, we will start with the introduction and motivation about the work, and then we're going to how we collect the data and also the methodology, how we evaluate the quality. And then we start looking into the experiments for different visual language models to see their performance, and we will end with conclusion. So let's start with the introduction of asking about this question. What food is this? So this is a picture of a food. You might able to guess what is this food called. They make some option that kind of they might be correct, maybe they are not. They might have some similar characteristic for some food in the options. And if you really know about this food, this is actually empanadas. Okay, looking back at the example we have, we want to evaluate visual language models with different food concepts that are actually similar and can be found across different countries. And we want to also highlight the problem in the research of computer vision and also natural language processing about evaluating the multilingual and multicultural capabilities of visual language models. And in this work, the goal is to create the first massive scale benchmark that consists of high quality multilingual, multicultural text image pairs. And all of them are highly annotated by native speakers in their local languages. So at the end of this research, we are able to answer whether visual language models have cultural awareness of food and also the world cuisines. Let's go to the methodology. Let's start with the overview. So world cuisine is an open source benchmark designed to evaluate the cultural relevance. And we are focusing on 30 different languages and dialects that spans to 9 language families. And also we feature the 1 million data points that we collected. So these are the statistics that we collected from the data that we generated. You can see we have 3 different data splits. So the training part is something we skip for future research. So we create 1 million datasets that later we can use it for fine-tuning. And for the evaluation, we prepare test small and test large. And these are the data that consists of 3 different languages and dialect. So they are all parallel and multilingual. And you can also see we have 4 different tasks. So for task one, we have 3 subtasks. They are now contextualized and adversarial, which I will discuss later. And for task two, we have location predictions. And in total, we collect 72,000 task data. And also for the training, we have about 1 million. Let's talk about each of the subtasks. For task 1A, we call it this name predictions. And you can see from the example that we have milk cream strudel picture on the right, on the left-hand side. And then on the text, you can see there are multiple choice and open-ended tasks in English and also Japanese. So we want to show you that we have parallel data between English and Japanese, and also for a language specific to script languages, we also try to find the script text for the dish names, like in Japanese. To make it more challenging, we not only look at multiple choice questions, but also open-ended questions. The second subtask is contextualized listening prediction. It focuses on helping the predictions of the visual language models by providing the relevant context. Like in this case, the food is actually coming from Brazil, so we add locations to help the visual language model to get the right answer. So for task 1C, we want to also make it a little bit more complicated and more challenging for visual language models by adding adversarial context. So if you read on the example, we provide unrelevant context to visual language models, and then we hope that the visual language model uh, is not grounded to the wrong context, but is still grounded to the picture that we provide. And in this case, the answer is egg Benedict, and egg Benedict definitely is not from Korean restaurants. In for task two, we look into location prediction. So for location prediction, we the task is to ask which location or country that made this dish popular. We have also different templates and ways to ask these questions. And in this case, we show some example in English and French to show you how the parallel data works together for this example. We also want to compare existing data with ours. You can see we are getting the highest number of VQA, and also we have 30 different language and dialect, which is one of the most richest data that are collected from the compared to previous existing data. And our data also are collected across different 189 countries. And we have the most food entries among other existing data. We have 6,000 images. Everything is parallel. And also the license is very safe for experimental research and also for commercial usage. We also want to provide some interesting facts. If you see this figure, you can see the top 10 food that we collected are coming from US, Japan, China, Indonesia, Philippines, Mexican, Indian, Italian, Spanish, and United Kingdom. It's a little bit long tail in terms of the lower end, but mostly we collected data from cuisines that are relatively richer in terms of the variety of the food. And also, this is a figure of map that you can see about the distributions of the food, and we realized that we actually not really representing well on African food, but mostly we represented well across Europe, Asia, and the US, and a little bit on the Australia and Oceania. Okay, let's go to the experiments. In the setting, as I mentioned, we have multiple choice question and open-ended question. And these are the results of the experiments. You can see in general, MCQ performance is higher than the open-ended, which just makes sense because it's harder to generate open-ended answers. And you can see the trend that when we add the right context, the performance it increase significantly. And when we provide adversarial context, the performance drop. And you can see that actually hurt the VLMs. And for the location prediction, relatively the the bigger model has get better results compared to the smaller models. And on average, the proprietary models are still outperforming all the baselines and also all the open source models, which means the open source models still need to catch up a little bit more on compared to the proprietary models. But the best open source model that we found is Llama 3.2 Instruct 90p. This is another result from different categories. You can see how the performance across different categories. Another analysis and results that we can provide from the paper. You can see the performance versus the model size. So you can easily see that Llama 3.2 is the best among all, but it's also the largest model. And also Quen 2 7B is relatively good for MCQ comparatively to the number of parameters it uses. And also Llama 3.2 11B is performing very well for open-ended cases, even comparing to the Quen 2 72B. Let's summarize and also discuss about the takeaways. This benchmark remains challenging for vision language models, particularly for dishes from specific regions and also for low research languages. We also found VLMs perform better with correct context and still struggle with adversarial context. And for the datasets, we are releasing a comprehensive knowledge base, also the VQA dataset for training and also for testing. And we also provide leaderboard for as a benchmark for open source resources. And we also want this dataset to be used for future research. Thank you for listening. These are the resources where you can get our food KV and also the QA and also the code for evaluation. Thank you.